Chemistry, we're on to our second and last lesson in Unit 8, Equilibrium. This is on a subject called Le Chatelier's principle and also a couple of other topics as well. So we're going to start off with the concept of reaction quotient, which is designated by the letter Q. So the reaction quotient Q is computed the same way as the equilibrium constant K, except Q is computed using the existing, not equilibrium concentrations. The reaction quotient is used to tell which way a reaction will flow. So if Q is equal to K, then that means the reaction is at equilibrium, and so it's not going to flow in either direction, towards products or towards the reactants. If Q is less than K, then the reaction has too many reactants for the products, and so it's going to flow to the right. It's going to flow from reactants on the left to products on the right. And that is said to favor products. That's the expression or the terminology used when a reaction moves from left to right, from reactants on the left to products on the right. It favors products. If Q is greater than K, then that means the reaction has too much product for the amount of reactant to be at equilibrium, and so the reaction has excess products and will create more reactants. This means it's going to move backwards. It's going to move from products on the right back to reactants on the left. And in this case, it is said to favor reactants. So favoring reactants means the reaction's moving to the left, it's moving back towards creating more reactants, and favoring products is moving to the right. It's going to create more products. So the reaction quotient Q is computed the same way as the equilibrium constant K, except Q is computed using existing, not equilibrium concentrations. So we're going to take the same reaction we used in the last lesson, and these are the reactant values. They're the same as in the previous lesson. We said there was 0.25 molar H2 and 0.5 molar of I2. In the previous lesson, we said there was 2.5 molar of the product HI. In this case, we're going to double that. So this product concentration is double the previous equilibrium value. Again, that's from the previous lesson, lesson 1. So we should expect the reaction to flow from products back to reactants. Why? Because it has the same concentrations of reactants, but now it has too high a concentration of product for that concentration of reactants. Remember, equilibrium is a balance where it's happy. It doesn't want to move either forward or backwards. But what we've done is we've opened the container and we've stuffed it in more HI than it likes to have at that equilibrium. And so it's going to want to move backward. It wants to decompose the HI and move back to creating more H2 and I2. So that's a reverse reaction. So we compute Q the same way as Kc. So we have the products on the top and the reactants on the bottom, and we use their coefficients as the exponents, so it's exactly the same as the previous lesson, except the difference is in this equation set up here, you see a 5.0 on top instead of a 2.5 as in the previous lesson. So now when we compute Q, we get 200. Q equals 200. So since Q is greater than the equilibrium constant, from the previous lesson, we computed that to be 50. The reaction will move in the reverse direction and reduce the concentration of products and create more reactants, increase their concentrations. Okay, Le Chatelier's principle. So Le Chatelier's principle states if a chemical system at equilibrium is disturbed by a change in the temperature, pressure, or concentration of one of the components meaning reactants or products, the system will shift its equilibrium so that it counteracts the effect of this disturbance. So remember, equilibrium is a happy place where the reaction likes to be. If you change something about that reaction, it's not going to be in equilibrium anymore, and it's going to want to shift so that it gets itself back into equilibrium. So if the reaction changes so that more products are formed, it is said to favor products. That's a review of the previous slide. If the reaction changes so that more reactants are formed, it is said to favor reactants. Okay, so the reaction below is initially at equilibrium. So if reactants are added or products are removed, the reaction will move towards products. That's a change in concentration. So let's say we add the reactants on the left, H2 or I2, or we remove HI on the right, then it's no longer going to be in equilibrium. So the reaction is going to want to move to create more HI. And that's going to favor products. So I use a metaphor of a crowded room. If my classroom and Mr. Andrews' classroom have certain numbers of students, and we're happy, everybody's happy with the number of students, and then all of a sudden you crowd more students into my classroom, then students are going to want to move over to Mr. Andrews' classroom. It gets too crowded in my classroom, they want to move over to Mr. Andrews' classroom. If by contrast you took students out of Mr. Andrews' classroom, but my students stayed the same, my students would still want to go over to Mr. Andrews' classroom because it's not very many people in there. We've taken people out of there. So the students in my room want to move over to his room to balance things out again. So think of it like a crowded room. People want to move away from a crowded room, or they want to move towards a more empty room where they have more space. And the same thing is happening in this reaction. So if reactants are removed or products are added, the reaction will move towards the reactants. It will move backwards. So we remove some H2 or I2. You don't have to remove them both. You just remove one or the other or both. Or you add HI. Now all of a sudden the room on the right side is more crowded. The room on the left side is less crowded. And you don't have to do both of these at the same time. You don't have to remove H2 and I2 and add HI at the same time. You can just do one or the other. Then the reaction is going to move towards the emptier room, and that would be to the left. That would be toward H2 and I2. So that's going to favor reactants, the bottom reaction. Okay, now let's talk about heat, changing temperature. In an endothermic reaction, heat is treated as a reactant. So heat pushes the reaction to favor products. In other words, you treat heat, if a reaction wants to take in heat, that's what an endothermic reaction is, it wants to take in heat, then if you add heat, the reaction likes that. If it wants to go from left, that's H2 and I2, over to the right, to HI, if you add heat, it will help it to do that because it is an endothermic reaction. It wants to take in heat. So adding heat will move the reaction to favor products, that is from left to right. That's if it's an endothermic reaction. In an endothermic reaction, if heat is treated as a reactant, so heat removed pushes the reaction backwards to favor reactants. In other words, you're taking away one of the things that reaction wants. It wants more heat. It's endothermic. So if you actually remove heat, it's going to slow the reaction down or actually cause it to move backwards from right to left. So that's going to favor the reactants. And that favors reactants. So that's for an endothermic reaction. Now if it's exothermic, let's take a look at that. In an exothermic reaction, heat is treated as a product, so heat removed pushes the reaction to favor products. So that reaction, if it's an exothermic reaction, by the way, the same reaction can't be both endothermic and exothermic. I'm just keeping the same reaction to keep things simple. Let's just say it's an exothermic reaction. That's negative delta H, negative enthalpy. That means heat will come out of it. So if you remove heat, that's going to allow the reaction or cause the reaction to move from left to right to favor products. Now, if it's an exothermic reaction and heat is treated as a product, so heat added makes it more difficult for heat to exit and pushes the reaction back to favor reactants. So this one's a little harder to kind of conceptualize, but just remember, this reaction, if it's exothermic, wants to give off heat. But what you're doing is you're doing something it doesn't like. You're pushing heat into it, into a reaction that likes to give off heat. So that's going to slow the reaction down going from left to right. So that means it's going to want to either slow down or move backwards, move in the reverse direction towards the H2 and I2, and so that will favor the reactants. Pressure. So pressure increase caused by changing volume for gases only. So the reaction below, we'll use a different reaction, has 1 mole on the reactant side and 2 moles on the product side. So there's 1 mole of N2O4 and there's 2 moles of NO2. So it has twice as many moles on the right side as on the left side. So if pressure is increased, the reaction will try to return to equilibrium by reducing the number of moles, which will reduce the pressure. This can be done by turning products back into reactants in the reaction above. This one you have to think about a little. Okay, it has a certain amount of pressure right now. All of a sudden you increase the pressure, say by squeezing down the volume, making the volume smaller. You got to kind of picture PV equals nRT in your head. So you've increased the pressure by some means, it doesn't matter how. The reaction is not happy because the pressure is too high. Now, if you look at PV equals nRT, if you reduce the number of moles on the right side of PV equals nRT, you will reduce the pressure on the left side of PV equals nRT. Reducing the moles reduces the pressure. And that's what the reaction will want to do. You've increased the pressure. So now it's saying, I'm not happy, the pressure's too high. So the way it has control of that it can reduce the pressure is by going from 2 moles on the right back to 1 mole on the left. 1 mole will have less pressure than 2 moles. That's just from PV equals nRT. So if you increase the pressure, here's the rule. If you increase the pressure, the reaction will want to move in the direction of the side that has fewer moles. So since N2O4 has fewer moles than 2N2, the reaction will want to move back because it's making the room less crowded. By squeezing up the pressure, you made the room more crowded, and now it's going to want to move to make the room less crowded, so it's going to try to create fewer moles, and it does that by going from 2NO to 1 N2O4. If the pressure is decreased, then the reaction is going to say, I'm not happy because there's not enough pressure in this vessel. So it will try to return to equilibrium by increasing the number of moles. If it increases the number of moles, that would increase the pressure. Okay, so that way, in that case, it wants to move from the left to the right, from 1 mole of N2O4 to 2 moles of NO2. So let me read that bottom sentence again. If the pressure is decreased, the reaction will try to return to equilibrium by increasing the number of moles, which will increase the pressure. This can be done by turning reactants into products, 1 mole to 2 moles in the reaction above. So again, to summarize, if you increase the pressure, it wants to lower it back down so it's at equilibrium again. That means it will want to go from the side that has more moles back to the side, or forward, whichever way, to the side that has fewer moles. If you decrease the pressure, it wants to increase it again to get back to equilibrium, so it will go from the side with fewer moles to the side with more moles. So PV equals nRT. Increased P increases the side with fewer moles. Decreasing P increases the side with more moles. That's what the reaction will do to counteract the change in pressure. Okay, so the graphs below are called energy diagrams. For a reaction to take place, energy must be put into the reactants to break the chemical bonds. So what happens is you see the reactants on the left, and in all chemical reactions you initially have to put in energy. So that's what you're seeing with the red arrow on the left. It's actually the energy is going up initially, and it gets on top of what's called the energy hill. That's what they simply call it, the energy hill. And then it has to get over the energy hill to create products. Okay, now when bonds are formed and the products are being created, they're going to a lower energy state, so they're releasing energy. And that's what you see in the red arrow on the right. So the bonds are formed when the products are created. This releases energy. Now you'll notice these two graphs are a little different. One of them, the products ends up higher than the reactants, and the other, the products ends up lower than the reactants. So let's examine that. If the final energy state of the products is higher than the reactants, then the reaction is endothermic. In other words, it ended up with more energy than it had at the beginning of the reaction, and therefore that's an endothermic reaction. Energy had to go in. Heat energy or some sort of energy had to go in. If the final energy state of products is lower than reactants, then the reaction is exothermic. Heat energy came out, or energy came out. So the one on the left is an endothermic reaction because the energy of products is higher than reactants. The one on the left, the one on the right is exothermic because more energy came out than existed at the beginning. So equilibrium exists when the rate of the forward and reverse reactions are equal. Okay, that's a concept we skipped over, so anyway, you don't have to worry about that. This will happen at a particular activation energy. That's energy is the difference between where the reactants were at the beginning and the top of that hill. So it's what you see as EF on the left side of that graph there. That's the activation energy to get this reaction to get started. When a catalyst is used, the activation energy of a reaction is lowered. Lowering activation energy increases the rate at which the reactants are converted to products, but not the amount of reactants and products. So catalysts do not change the value of equilibrium constant. So what a catalyst does is it speeds up a reaction. In biology, catalysts are called enzymes, and they speed up the speed of a reaction, how fast a reaction takes place. That has to do with the field of kinetics. We didn't do what you actually saw that when we put the glow sticks in the ice water and then in the hot water, the reaction was speeded up. That wasn't due to a catalyst, that was due to a change in temperature. So what you need to simply understand is that's what catalysts do. They speed up how fast a reaction takes place, but they do not change the equilibrium value of how much products and how much reactants you'll have at the end of the reaction. You just get there faster. Okay? So catalysts speed up a reaction. Okay, and that takes care of this lesson, and that's our last lesson in the subject of equilibrium.